Every second, a whopping 40 kilograms of water is streaming away. That's what NASA's Swift telescope picked up from Comet 3I Atlas during late July and early August. And this wasn't even at its closest approach to the Sun. No, not when the comet was brushing against the Sun and soaking up the peak solar energy. We're talking about a distance of 2.9 Australian dollars, nearly 3 times Earth's separation from the Sun, where you'd expect water to hardly vaporize at all. Yet in under 3 weeks, it slips behind our star, out of sight from every Earth-based observatory, just as the action ramps up the most. If you're keen to know what unfolds next, smash that like button and subscribe. Drop a comment below. Where are you tuning in from? What's the local time? And do you reckon this is merely intense cometary outgassing or something more intriguing? Chapter 1. The Mystery of the Fire Hose. The Swift data, released on September 30th in the Astrophysical Journal Letters, isn't just odd. It's shattering expectations. Dennis Bodwitz and his colleagues at the University of Maryland dedicated more than 2 hours to layering ultraviolet images, zeroing in on the hydroxyl signal, that distinctive shimmer when solar rays split water molecules. Their discovery revealed a rate of mass ejection that laughs at models based on distance. At that far out from the Sun, comets usually exhibit just 3 to 5% of their surface actively venting. But 3I Atlas? At minimum 8%, almost twice the norm. Here's the really puzzling part. The numbers don't add up for straightforward surface evaporation, not even factoring in the Sun's warmth at 2.9 Australian dollars. The available energy simply can't account for 40 kilograms per second venting from a core roughly 5 to 6 kilometers wide. Unless there's more at play. Observations in the near-infrared from Gemini South and NASA's Infrared Telescope facility offered clues. Ice fragments drifting within the coma, not merely gas. Real bits of frozen water hanging in the hazy envelope around the nucleus. When these pieces catch even faint sunlight, they warm quicker than the solid surface ice thanks to their greater surface-to-volume ratio. Each turns into a tiny geyser. With hundreds or thousands dispersed across the coma, they all add to the overall water release. This makes the nucleus appear way more productive than it truly is. Zishi Xing, the principal investigator, summed it up neatly. Every interstellar comet we've encountered has thrown us for a loop. Oumuamua was parched. Borisov overflowed with carbon monoxide. And now Atlas is relinquishing water far beyond where we'd anticipate. Each discovery is reshaping our understanding. But what sparked those ice fragments to begin with? Did 3I Atlas undergo some breakup episode prior to our spotting it? Is this rubble from eons of tiny meteoroid strikes on its long interstellar trek? Or do comets originating from the galaxy's thick disk operate this way by default, their makeup entirely alien due to formation in environments unlike anything in our solar system? The schedule complicates things further. 3I Atlas dropped out of Swift's sight in August, too near the Sun for secure viewing. Yet come early October, ESA's Mars Express orbiter snagged images during a pass at 30 million kilometers. The coma stood out plainly, spanning several thousand km, confirming the outburst persisted. The comet keeps bleeding water vapor as it nears its solar closest point. And that's key. Nears, because currently, 3I Atlas is diving into solar conjunction. With Earth and the comet flanking the Sun on opposite sides, no terrestrial scope can pierce the blinding light. It'll hit perihelion on October 29th at 1:36 Australian dollars, snug inside Mars' path, totally obscured from us. The solar flux there will dwarf what Swift measured by magnitudes. If 40 kilograms per second marked the norm at 3 Australian dollars, imagine the surge at 1.4. Standard models predict the obvious. The comet ought to flare up brilliantly. Its coma would balloon. Hypervolatile ices, stuff like CO2 and CO that turn to gas at cooler temps than water, should burst forth. The tail could stretch into a dazzling ribbon, millions of km in length. We've witnessed this cycle countless times in our own system's wanderers. Yet 3I Atlas has already bucked the norms. That water surge at 2.9 Australian dollars? Unforeseen. The 8% active area? Off script. The frosty rubble cloud in the coma? Total surprise. So the drama of its concealed perihelion swing remains a true wild card. ESA's JUICE probe will snag the prime vantage from November 2nd through 25th. Once 3I Atlas swings clear of the sun's shadow, JUICE will scan it using imagers, spectrometers, and detectors for particles. Its position is ideal, distant enough for clear views, yet near enough to dissect the aftermath of perihelion up close. The catch? Data relay. JUICE is deploying its high-gain dish as a thermal barrier for now, falling back on a low-speed secondary antenna to beam info home. Those November glimpses won't reach us until February 2026 marks the end of a tense 3-month vigil. For those months, uncertainty hung heavy. Did the comet make it through perihelion unscathed? Did it break apart like Shoemaker Levy 9 caught in Jupiter's gravitational pull? Or did some unforeseen event unfold in the obscured period trailing the sun? There's one overlooked angle, casually noted by Dennis Boditz without much fanfare. In comet research, water serves as the ultimate benchmark. It gauges activity levels and hints at underlying makeup. Yet 3 Atlas isn't a homegrown solar system wanderer. It's an envoy from a distant star's planetary realm, possibly born 10 billion years back in our galaxy's dense disk. The primordial cloud that spawned it featured distinct temperatures, varying mixes, and unique chemical layers compared to the disk that birthed Earth and Jupiter. The water we're spotting could match our hydrogen-oxygen combo in structure, but its origins scream otherworldly. Isotope proportions, embedded trace materials, even the ice's crystalline form, they all encode secrets from a stellar setup we'll never reach. Swift picked up hydroxyl, the shattered byproduct of water. Still, hydroxyl might stem from diverse source molecules. Think organics, alcohols, or intricate reactions in the coma where solar rays and cosmic particles dismantle bigger compounds into bits. That 40 kilograms per second rate could be straight H2O or a blend of water alongside other evaporating substances mimicking the same spectral lines. To pin it down, we require sharper spectral analysis. We need extended viewing sessions. Above all, the comet must endure perihelion and keep venting as it swings outward to interstellar voids. That's the harsh truth. 3 Atlas won't return. Once it zips by Jupiter in March 2026, it's gone for good. This represents our sole shot at probing a comet from the galactic thick disk, a cluster of ancient stellar domains untouched by prior surveys. No observation is trivial. Each data morsel is priceless. The gushing water stream is merely the prelude. It signals that 3I Atlas brims with volatiles, boasts an odd structure, and spews gases at ranges where local comets stay quiet. But the real drama unfolds over the coming month, concealed behind the sun, out of sight, where comet norms might hold firm or crumble utterly. Then, when JUICE secures its readings in November, as the comet reappears bearing perihelion's full impact, we'll learn if this water ejection was a teaser or an alarm. We'll determine whether 3 Atlas is simply a hyperactive oddity or a discovery demanding a total overhaul of comet lore. The resolution lurks unseen, just 50 days from unveiling. Chapter 2. Lowe's Mothership Idea. The Loeb scale score leaped from 4 to 6 within 2 weeks. That's no minor tweak. On a spectrum from 0, purely natural, to 10, unmistakably artificial, a shift like that signals a major reevaluation of likelihoods. And Lowe isn't prone to such adjustments casually. Every notch demands hard evidence, measurable oddities, data points defying standard interpretations. By mid-August, 3I Atlas had piled up sufficient quirks to nudge the gauge into realms that unsettle most sky watchers. Let's kick off with the trajectory odds, often quoted yet routinely brushed aside. A mere 0.005%. That's the chance an inbound interstellar body would skim so near Venus, Mars, and Jupiter. Or 5 out of 100,000. Lowe's group crunched this via orbital dynamics and alignment slots, factoring in planetary motion and slim approach margins. The calculations are basic. A retrograde hyperbolic path from Sagittarius direction creates narrow probability funnels for each planet flyby. The odds of nailing all three? Practically nil. Detractors claim it's hindsight bias, that scanning enough interstellar intruders, one will luck into a rare path eventually. Fair point, but we've spotted only 3 such visitors total. And this one neatly aligns to graze the inner solar system's prime rocky targets. The baseline assumption for that, sans other clues, feels downright uneasy. Layer on the perihelion schedule. October 29th, smack in solar conjunction, with Earth and 3I Atlas flanking the Sun's far sides. Ground telescopes go blind right at the pivotal moment. If aiming for a thrust adjustment, an orbital velocity tweak via burn, perihelion's prime real estate. You're hurtling at peak speed sunward, so each unit of fuel packs maximum punch. The minimal change in velocity is known as the Orth effect. Space vehicles rely on it all the time, and 3I Atlas hits its closest point to the Sun exactly during the period when it's hidden from our view. Low figured out the velocity shift needed for tiny probes launched at that closest approach to enter Earth's orbit. The calculations check out. A compact probe, say around 10 kilograms, equipped with a chemical engine boasting a specific impulse of about 300 seconds, could execute an inverted Orth maneuver and settle into a reliable path around our planet. The timing for arrival falls in late November through early December, just as 3I Atlas swings out from the Sun's glare, and we begin scanning for alterations after its perihelion pass. Could this be the strategy? Or is there no strategy at all, and we're just spotting designs in chaos because people love finding connections, especially since Loeb has tuned our minds to hunt for these very signs? The mismatch in dimensions still puzzles everyone. Initial light readings pointed to a 20 kilometers core if the reflectivity matched average asteroid levels. That's ridiculously huge for something from beyond our system. Oumuamua measured only a few hundred meters across. Boris topped out below a kilometer. A 20 kilometers comet dropping into our neighborhood would defy all odds statistically. The sort of rarity that defies happening within one person's lifespan. Yet Hubble's views of the surrounding haze revised those figures downward. Now it's estimated at 5 to 6 kilometers, drawing from the core's own glow compared to the overall light from the dusty envelope. That's still sizable. Still odd, but plausible enough for something formed naturally. Except those first brightness observations weren't off base. They were spot on. 3 Atlas truly shone brighter than expected for a 5 kilometers comet at such a range. Low proposes high reflectivity. If the exterior includes metal elements, if the form channels sunlight efficiently, if the composition strays far from typical fluffy ice and grit, then you end up with unexpected luminosity. You end up with something that seems larger than reality. That might occur in nature. After all, metal-rich asteroids are out there. But when stacked with all the other clues, it tips the scales toward higher chances of something engineered. Next comes the setup of the dust. Hubble's snapshots reveal the thickest concentration of particles facing the Sun. The hefty bits, those too weighty for solar radiation to shove aside, cluster in front of the core along its path. Normal comet venting ought to create streams shooting straight out from the surface, guided by where the heat hits hardest. Such streams could aim anywhere, shaped by the spin axis and the spread of frozen gases. But ongoing dust blasts toward the Sun demand either an oddly aligned spin or another factor at play, something that keeps pushing out matter forward no matter which side greets the sunlight. Low notes this aligns with debris kicked up from barreling through interstellar gas at high speeds. If 3I Atlas has been cruising at 60 to 70 kilometers per second over eons, collisions with hydrogen atoms scattered in space aren't negligible. Every hit dumps energy. Rack up enough, and the front face starts wearing down. The dust we're observing might stem from those collisions. Stuff steadily sheared away by the onslaught of interstellar drag as the thing cuts through the void. That's a straightforward natural account, yet it also fits with exhaust from onboard mechanisms, where steering jets hold the pose steady amid various tech operations yielding the same visible effects. The spin cycle of 16. 16 hours lands smack in the gray zone. Not rapid enough to whip up from gas release, not sluggish enough to sink neatly with any external pull. For a loose aggregate comet bound by feeble gravity, that spin feels steady and ordinary. For a sturdy body, whether born in nature or built, it's just as steady and ordinary. It reveals zilch conclusive, but the incoming trajectory proves tougher to brush off. Originating from Sagittarius places it against the galactic core, the densest, most luminous patch in the heavens. Picking it out amid that glare is incredibly challenging. We only caught 3I Atlas thanks to the Atlas Survey's telescopes, built to snag quick movers, and even so, it almost slipped by. Archive shots trace back to mid-June, but weeks before, at magnitude 20, it was hardly detectable, and we'd have zero data otherwise. It would have zipped through the inner system without a trace. For a scouting run into an unfamiliar star system, entering via the galactic hub makes strategic sense. You show up cloaked in the stellar backdrop, offering the locals scant heads-up. By detection time, you're embedded far inside, rendering any reaction pointless. Did that unfold here, or are we again weaving purpose into mere chance? The initial spectral mix-up throws in yet another clue. Several groups found no carbon compounds in the opening observations. No obvious water traces, merely rusty particles and unclear spectral dips. It seemed lively, yet not like a classic comet. Lowe contended that Clincher was the undeniable evidence showing that 3I/Atlas wasn't acting like your typical comet. Additional data soon followed. Traces of water appeared. The surrounding haze was mostly carbon dioxide. The light patterns began aligning with what we'd expect from a comet. Lowe adjusted his stance, though he pointed out the early uncertainty still lacks a clear explanation. What delayed the emergence of those usual icy gas signals? Why the initial mix-up? A likely culprit could be flaws in the observations. The first readings used coarse, quick scans while the comet remained dim. Once it grew brighter and sharper tools zeroed in, the results sharpened up. The apparent lack of gases was merely a matter of weak data quality. That's the straightforward explanation. It's likely spot on, yet likely carries a heavy load here. Lowe isn't asserting total confidence. He's stressing that the chance isn't nil. That overlooking a possible artificial object as mere space rock, given how plentiful comets are compared to engineered relics, could shatter our grasp of cosmic intelligence. He urges the Galileo Project's facilities to scan for follow-up clues through November and December. Should 3I/Atlas dispatch any subunits? And if those enter our atmosphere for a detailed look at Earth, we might notice a surge in unexplained flying objects. Items zipping along in patterns that buck normal flight physics. Echoes on radar that don't fit rocks or our own tech. Is this probable? Hardly. Lowe concedes the scales tip toward a regular comet, but they're not locked at 100%. And in that sliver between strong likelihood and ironclad proof thrives the whole domain of searching for alien tech signs. For 6 decades, we've tuned in for radio chatter from extraterrestrial societies. We've erected giant scopes to snag laser pulses from far-off suns. We've pored over countless starlight profiles hunting for life traces in alien worlds' airs. Yet we've barely entertained the idea that relics could visit us. That wanderers from other stars, the kind we've only begun spotting over the past 8 years, might mix probes with plain stones. 3I/Atlas serves as the proving ground, the specimen pushing us to craft ways to tell organic from made at vast cosmic ranges. Such techniques are absent right now. Sure, we have light variations, chemical profiles, and path breakdowns, but no solid system to declare this one's surely natural or that one demands a deeper dive. Lowe's working to forge that system on the fly, treating 3I/Atlas as his benchmark. The idea of a central carrier vessel is sleek yet chilling. You wouldn't dispatch a single scout to a lone sun. Too wasteful. Instead, you launch parent craft on gradual paths linking promising stellar clusters. Each hull scores or hordes of tiny scouts. Upon nearing a setup, it deploys customized units for targeted world checks. Those scouts are disposable, compact, easy to produce. The parent presses onward to the subsequent system and beyond, charting the galaxy across eons. To its creators, the payoff is massive. A single parent could probe thousands of realms, and we'd miss its approach entirely. The parent would stay shadowy, frigid, blending with comets or boulders until deployment began. At that point, it's over. The scouts are loose, nearing goals, and even spotting them wouldn't let us catch up. Not with today's gear, unless we had years to prepare. Lowe sketches a schedule. Suppose scouts launched on October 29th during the concealed solar close approach, employing backward thrust tricks to break and settle into Earth loop. They'd hit between November 21st and December 5th. We're eyeing items perhaps shoebox-sized or tinier. Our planet's orbital watch systems catch down to roughly 10 centimeters in close orbits. But that's for anticipated stuff and set paths. An intruder from deep space, with built-in drive and steering smarts, could slip right past. Would they reach out? Stay stealthy? Circle above to observe, touch down, or just watch and transmit findings? Those puzzles haunt Lowe's sleepless hours, as the responses shape our fate. If they're benign seekers, the relic hunters of some old stellar empire, initial encounter might rank as humanity's pivotal instant. If they're otherwise, if the Grim Woods theory holds and broadcasting your spot invites doom galaxy-wide, we could already be past the point of no return. The Galileo project setups will keep vigil. 3 locations, round-the-clock scans, blanket sky watch. Any oddities observations made during the November-December timeframe will be recorded, examined, and shared publicly. Should no events unfold, if 3I/Atlas acts like a typical comet with no incoming probes, the theory's validity diminishes. The assessment score for the Loeb scale falls once again. We'd categorize 3I/Atlas as intriguing yet ordinary and proceed accordingly. However, if events do occur, if we spot anomalous objects in positions they shouldn't occupy, traveling along improbable paths, materializing precisely as Loeb forecasted, then we're facing either a challenge or a breakthrough, based on subsequent developments. Chapter 3. October 29th, Hidden by the Sun. This solar conjunction shouldn't unfold with such intensity. Comets routinely swing behind the sun, vanishing from sight for several days or weeks before reappearing on the far side, altered in foreseeable ways. More luminous if intact, broken apart if not. For generations, astronomers have observed this cycle. We anticipate the outcomes. Yet 3I/Atlas will hit perihelion at 1:36 astronomical units on October 29th, fully obscured by the sun's blinding light. The ensuing unpredictability is propelling the field into unfamiliar ground. The setup is unforgiving. With Earth and the comet positioned on contrary sides of the sun, the angle prevents any earthbound viewing. Directing a telescope toward something just 12 degrees from the sun risks ruining the equipment or overwhelming the sensors. The sun's radiance drowns out all else. Even orbital observatories like Hubble adhere to rigid no-go zones near the sun. Instruments such as SOHO and other coronagraphs could offer a brief look, but 3I/Atlas is projected to be too dim, too distant from the sun's edge, to stand out amid the diffused glow. For about 6 weeks, spanning early October through mid-November, we're essentially sightless. Perihelion involves more than just observation. It's rooted in physics. At $1.36, the sun's energy is potent enough to evaporate all unstable materials on the comet's exterior. Water ice turns to gas with fierce speed. Carbon dioxide, identified as the main gas in the surrounding haze from JWST data, shifts from solid to gaseous form in a flash. Carbon monoxide, ammonia, methane, along with any ultravolatile substances locked in the ice, burst free all at once. The core turns into a high-pressure vessel. Gases jet out via fissures and openings, dust rises on the rising vapors, and the haze balloons to millions of kilometers. The tail trails extended like a flag. That's the standard prediction, straight from the manuals. This framework relies on our grasp of 3I/Atlas's makeup and build, which remains incomplete. JWST observations on August 6th uncovered a surprise, an 8:1 proportion of carbon dioxide to water. That's one of the most elevated ratios documented in comets. Typical ones from our solar system display balances nearer to 1:1 or even water-heavy profiles. Carbon dioxide appears often, but seldom leads as the key volatile. 3I/Atlas inverts that dynamic. It's primarily a dry ice body, with water playing a supporting role. This alters predictions for perihelion entirely. Dry ice from carbon dioxide sublimates at far cooler temperatures than water ice. At $1.36, the sun-facing surface might climb to 200 Kelvin or beyond. That's plenty above CO2's activation threshold of about 150 Kelvin. Water ice, by contrast, requires roughly 270 Kelvin for steady sublimation. Thus, a separation emerges. CO2 blasts away from the surface right away. The water, embedded below or blended within the ice, releases at a more gradual pace. This yields a phased gas emission process, an initial explosive CO2 surge that forms a vivid, swiftly growing haze, followed by a steadier flow of water vapor as erosion reveals inner layers. Yet complications arise. If CO2 prevails and erupts with force, it might strip off the dusty outer shell that shields the water ice beneath. Without that barrier, sunlight delves further in. Water evaporation ramps up. The comet might shift from CO2, lead to water-lead dynamics within hours or days. And we'll miss the spectacle entirely. JUICE will only capture the results come November. There's a further possibility, avoided in official publications but murmured in private discussions: disintegration. The strains of perihelion are tangible. Thermal jolts, gas buildup inside, and the sun's gravitational pull can rip fragile bodies asunder. History bears this out. Shoemaker-Levy 9 broke into over 20 fragments prior to Jupiter's collision. Comet Biela fractured in the 1800s and stayed in pieces. Closer to now, Comet Atlas C/2019Y4 crumbled in 2020 nearing the Sun, dissolving into scattered rubble. 3I/Atlas spins every 16 hours, a pace leisurely enough to dismiss spin-off risks. Its own pull ought to keep it cohesive. But the body has journeyed across the void between stars for billions of years. Exposure to cosmic radiation, extreme temperature swings from nearly absolute zero up to the heat it soaked up while gliding past distant suns, collisions with tiny meteoroids, and hollow spaces forming inside from the evaporation of volatiles across eons. We might not spot any weaknesses in its framework through spectral analysis or brightness measurements. Should it break apart, the pattern of its light output would reveal the truth. A quick surge in luminosity as fresh surfaces come into view, followed by a sharp dimming once the pieces spread out and the overall reflecting area shrinks. When the JUICE probe takes a look in November, we'd likely observe several chunks with distinct cores, each trailing its own envelope of gas and dust stretched along the trajectory. From a research standpoint, that would be thrilling. Access to various intersections of an interstellar comet, unveiling diverse strata and revealing chemical variations throughout. Yet it would also signify we overlooked the actual splitting moment. The breakup itself, the stresses at play, how the components pulled away. None of that unfolded in our line of sight, hidden on the sunward side where documentation was impossible. On the other hand, there's Lowe's idea, viewing closest solar approach as a chance instead of a risk. Should 3I Atlas be artificial, equipped with any drive systems or deliberate steering, that's the prime time to engage them. Solar gravity boosts every unit of push. A brief firing near the sun generates speed adjustments that would demand vastly more propellant farther out. If the aim involves deploying scouts to loop around planets, this is the spot to launch them. The calculations leave no doubt. October 29th marks the ideal time frame. Lowe worked out the precise details. A 10 kilograms device powered by a chemical engine delivering 500 meters per second change in velocity could settle into a stretched Earth path, with its low point at about 400 kilometers and high point past the moon. Positioned there, such a scout might examine our planet's air layers, seas, radio signals, or any orbital visible features. It could beam findings back to 3I Atlas prior to the main craft departing the solar system. Alternatively, it might stay quiet, monitoring, logging data for eventual collection. The entry period falls in late November, from the 21st through December 5th, based on precise launch spot and path. This presumes the devices apply only light tweaks on route. With extra propellant or advanced navigation, that time frame broadens. We might detect them sooner or later, or overlook them if they adjust course to evade notice. And now the troubling inquiry. Would we identify them at all? Our orbital monitoring setup catalogs known items. Orbiters, junk, discarded boosters. We predict their positions via gravitational rules. An unforeseen item in an odd path would set off warnings. But reactions aren't immediate. While we pinpoint the oddity, trace its source, dismiss organic causes, the device might finish its key tasks and shift paths anew. Lowe has directed the Galileo Initiative stations to watch for precisely this. 3 locations conducting non-stop scans of the entire sky in visible light, heat signatures, and radio bands. Any brief occurrence or item following paths that buck typical freefall paths gets marked for review. In the November-December span, they'll dial down the alert level for catches. More false alarms, sure, but heightened alertness too. If anything shows up, they'll catch it. NASA and ESA haven't publicly addressed this angle. Their emphasis stays on the comet as natural body theory, though privately, experts are tuning in. Space organizations maintain procedures for unknown items, not extraterrestrial protocols or invasion plans, but technical guidelines for unforeseen wreckage, unlisted craft, collision threats. These can flex to fit. If something pops into Earth orbit without a launch record, catalog listing, or believable cosmic source, the steps kick in. Surveillance ramps up. Defense resources join. Global players begin probing. With this broadcast airing, October 29th sits just 6 days off. 3i Atlas has vanished already, lost in the sun's blinding light. Final Earth telescope views came in late September. Mars satellites snapped it on the October 3rd close pass, but those shots depicted a standard comet. Clear gas tail, particle ejection matching sun warmth, no oddities hinting at machinery, breakup, or trouble. Still, perihelion changes everything. That's when heat strain maxes out, when built-up forces surpass material strength, when choices occur. If choices exist, in 6 days 3i Atlas will hug the sun nearer than across its whole multi-billion-year span. Surface heat will soar. Gas release will surge wildly, and we'll witness none of it. The SolLive updates will data from heliospheric observatories might still pick up traces of it. The Parker Solar Probe isn't in an ideal spot for this. However, Stereo and SOHO could possibly record some activity. Look for scattered light signals or variations in brightness. Should 3i/Atlas unleash a significant flare-up, or if its coma swells quickly, the Solar Sentinel satellites may spot shifts in the reflected sunlight. Such detections would be indirect, lacking sharp detail, yet they'd offer a valuable marker amid the data blackout. Next, we anticipate results from JUICE. That probe sits in an optimal location for views just after perihelion. From November 2nd through 25th, it'll deploy various tools for study. The Janus imagers will snap pictures, the MAGI spectrometer will probe chemical makeup, the PEP sensor will gauge the cometary atmosphere, and the UVS device will hunt for key volatiles. Everything trained on 3i/Atlas as it swings out from solar seclusion. Still glowing from the close solar encounter, possibly broken apart, maybe sporting an impressive tail, or perhaps behaving in unforeseen ways. Yet the information won't reach us until February 2026. JUICE currently deploys its high-gain antenna to block heat, depending on the medium-gain one for signals. Upload speeds are limited. Recording comes before sending, so photos and readings accumulate on board, queued for transfer when capacity frees up. When those November sites finally beam down, 3i/Atlas will have zipped beyond Venus, en route to the outer asteroid zone, already dimming and receding. A 3-month delay means endless debate, rival theories, and heated discussions. Did it endure? Did it shatter? Was there any oddity in that concealed solar skim? The truth lingers now in light packets racing from JUICE to our planet at full velocity. But it's out of reach. Knowledge stays locked until the files land, undergo review, and enter public access. That's the price tag for probing at cosmic scales using inner solar system explorers. We gain extraordinary perspectives from rare angles, but the toll includes delays, anticipation, and doubts that drag on for months rather than mere hours. October 29th marks the pivot. Prior to then, 3i/Atlas remains a sunbound comet, curious yet predictable, engaging without appending paradigms. Afterward, it transforms into whatever the perihelion wrought, perhaps a shattered rubble stream, or a vividly illuminated body with an enormous appendage, or a quiet survivor unscathed but subdued, or an entirely novel entity demanding fresh classifications, updated lingo, and revised analytical models. The sun conceals the revelation, not eternally, merely sufficiently to render the suspense excruciating. Chapter 4. The CO2 Enigma. On August 6th, the James Webb Space Telescope turned its gaze to 3i/Atlas at $3.32 from the Sun. The NIRSpec tool, built to snag infrared traces beyond visible wavelengths, gathered spectral data from 0.6 to 5.3 micrometers. The findings weren't merely quirky. They revealed a molecular signature absent from every comet in our records. a 7.6 to 1 ratio. That's carbon dioxide to water. To put it in perspective, the highest prior value, aside from the wildcard C/2016 R2, falls under 3:1. 3I/Atlas doesn't simply boast ample CO2. It's overwhelmingly ruled by it, in a way that upends our ideas about how comets assemble. Martin Cordner of NASA Goddard headed the review group. Their report, posted to AR-14 in late August, spells out the details. Enhanced vapor release appears on the sun-facing flank, just as solar warmth predicts. Water exists. Carbon monoxide shows up. Carbonyl sulfide emerges in preliminary spots. Water ice gleams in the spectra. Dust reflectance appears in near and mid-infrared. Everything routine. Everything aligning with typical comet traits, save for that ratio. At 7.6:1, it's 4.5 sigma beyond the baseline for long-period and Jupiter-orbit comets at comparable solar distances. Statistically, sigma tracks deviation from the norm. 1 sigma means everyday scatter. 2 sigma warrants attention. 3 sigma signals scarcity. 4.5 sigma indicates a major glitch or a core divergence. With shifts that extreme, you begin doubting if your benchmark dataset even applies. Perhaps 3I/Atlas isn't the odd one out. Maybe it represents a whole new class, and we're pitting oranges against entities beyond produce. The carbon isotope proportions provide further hints. JWST spotted carbon 12 and carbon 13 in the outgassed material. Their balance matches levels seen on Earth and across the solar system. This implies the carbon arose in a familiar stellar setting, not from primordial triple-star systems with scant metals, nor from a carbon-rich giant forged in exotic fusion. Simply standard carbon from an ordinary sun. Yet the heavy CO2 tilt versus water narrates a contrasting tale about scientists remain puzzled about the origins and formation process of the ice in 3I/Atlas. Two main theories attempt to account for this, though each faces significant challenges. The initial hypothesis centers on radiation exposure. Should 3I/Atlas have originated within a protoplanetary disk bathed in powerful ultraviolet light from a youthful, scorching star, or endured billions of years traversing the interstellar medium under constant cosmic ray assault, its water ice might have been selectively eroded. Water molecules prove more vulnerable to disruption compared to those of carbon dioxide. Energetic photons and particles strike the ice, severing the hydrogen-oxygen bonds, allowing the lightweight hydrogen to drift away into space. Leftover oxygen could then bond with carbon to yield additional carbon dioxide. Across vast geological timescales, a comet starting with abundant water might evolve into one dominated by carbon dioxide simply through relentless erosion. Yet this idea falters on the numbers. Achieving a shift from near parity between water and carbon dioxide to an 8-to-1 imbalance in favor of CO2 demands extraordinarily intense radiation over immense durations. We're looking at billions of years adrift in the interstellar void, devoid of any protection. This fits reasonably with 3I/Atlas's estimated antiquity. However, it presupposes the water ice stayed fully exposed on the exterior throughout. Should the comet possess even a thin dust mantle or internal features safeguarding deeper ice from radiation, the alteration process would plummet in effectiveness. A layering effect emerges. Outer ice undergoes heavy alteration, while inner ice stays untouched. As the comet activates and peels away outer layers, the proportions ought to fluctuate with fresher material surfacing. So far, no such shift has appeared. The proportions held steady from the August JWST readings to the prior SphereX results. The alternative theory revolves around the site's formation. Carbon dioxide solidifies at a cooler temperature than water. Within a protoplanetary disk, a demarcation known as the CO2 ice line exists. Closer in, toward the star, carbon dioxide stays as gas. Farther out, beyond that line, it freezes into ice. The water ice line lies nearer the central star. If 3I/Atlas assembled past the CO2 ice line in a disk unusually laden with carbon, it might have naturally pulled in more carbon dioxide relative to water right from the start of its buildup. This imbalance would lock into the comet's makeup immediately. Such a scenario calls for particular circumstances, a protoplanetary disk boasting an elevated carbon-to-oxygen proportion, or one whose thermal profile positioned the nascent comet in a CO2 ice-rich area, but water ice poor. Both possibilities exist. Stellar compositions differ, disk architectures vary, yet crafting conditions for an 8:1 ratio demands precise calibration. It points to a stellar system markedly unlike our solar setup. Uncommon, yet not out of reach. Data from SphereX in mid-August lends credence. This infrared space observatory spotted a vast carbon dioxide plume stretching over 348,000 kilometers from the core. No equivalent water plume at comparable distances. The CO2 jets out more vigorously, reaches greater extents, and shapes the coma predominantly. In contrast, water output stayed undetectable for SphereX, capped at roughly 4.5 kilograms per second. That's fully an order of magnitude less than Swift's reported 40 kilograms per second, which bore doubts due to observational range and techniques. This mismatch reveals key insights. Spotting water proves tricky. It hinges on precise wavelengths and tools. Swift picked up hydroxyl, a dissociation byproduct, rather than intact water. SphereX hunted for water's infrared emission signatures and found none. JWST did detect water, albeit in lesser quantities than carbon dioxide. Every instrument captures a distinct facet of the enigma. Harmonizing these demands guesses on chemical reactions, photodissociation speeds, and material spread. Guesses poorly grounded for an interstellar comet of mysterious makeup. A striking feature from the JWST observations emerges. Water emissions at 2.7 micrometers display uneven patterns. They don't spread evenly through the coma. Instead, vivid spots alternate with fainter ones, hinting at concentrated origins, possibly jets or enclaves of water-laden ice embedded within a CO2-heavy framework. When sunlight hits these zones, water bursts forth abruptly, not via constant evaporation. Spectral images thus appear mottled. By comparison, carbon dioxide emissions at 4.3 micrometers flow more steadily, blanketing the area uniformly, aligning with broad sublimation over the entire sun-facing side. This contrast in distribution signals deeper insights into the comet's makeup. Were 3I/Atlas uniformly composed of carbon dioxide ice, gas release would appear even. The localized water signals point to irregularity, fragments, strata, or inclusions of varying makeup, blended like rock formations bearing separate layers. Each stratum capturing a unique phase in the comet's history. The development or progression of the comet's structure isn't the sole explanation. With ongoing surface erosion, various strata become visible, leading to shifts in gas output to match. Yet an alternative view competes with this. The concentrated water release might originate from the frozen rubble zone within the coma. Those very particles that Swift spotted indirectly via hydroxyl signatures. Should these pieces vary in makeup from the core, if certain ones are abundant in water while others hold more carbon dioxide, the uneven patterns fit perfectly. No surface features on the nucleus are at play. Instead, the patterns emerge in the encircling haze. Countless or myriad ice fragments, every one a tiny comet analog, each adding to the overall emissions in distinct ways. To differentiate these views demands sharper imaging capabilities. Resolving the nucleus directly is essential to spot active zones, jets, or targeted outlets spewing gases. Hubble falls short. The core proves too tiny and distant. JWST can't manage it either. Its viewing field is overly restricted, and the comet races by too swiftly for thorough scans. JUICE could potentially succeed come November, provided the comet shines brightly enough, approaches near enough, and the instruments track accurately, though that's far from guaranteed. The detection of carbonyl sulfide, however provisional, introduces further complexity. OCS rarely shows up in solar system comets. It surfaces sporadically, typically in trace amounts, hinting at sulfur processes in the protoplanetary disk. Should 3I/Atlas contain detectable OCS, it implies sulfur was present in its birth system's planetary building phase. Paired with the prevalence of carbon dioxide, this sketches a stellar environment with atypical volatile balances. Elevated carbon levels, substantial sulfur, diminished oxygen, or at minimum, reduced water content. A setup favoring reduced molecules over oxidized variants. Why is this significant? Volatile compositions underpin potential for life. A system laden with carbon dioxide and sulfur, yet deficient in water, offers slim prospects for biology as we know it. Water serves as the essential solvent, the arena for chemical reactions in living systems. Carbon dioxide has its roles. Greenery harnesses it in photosynthesis, but it can't substitute for water. If 3I/Atlas originated in a water-deprived system, its planets would confront steep hurdles in fostering or preserving life forms. They'd be arid realms, flush with carbon but starved of moisture. The sort of worlds we're increasingly spotting orbiting M dwarfs, those compact red stars that outnumber others across the galaxy. Could that be 3I/Atlas's home turf? An M dwarf setup where the life-friendly zone hugs the star, tidal forces scorching one side while icing the other. Where hydration stays limited and carbon dioxide rules the air's makeup. Evidence of a thick disk birthplace bolsters this idea. Ancient stars, generally metal-poor but showing broad diversity. M dwarfs born 10 billion years back, steadily glowing to this day, as their orbiting worlds adapted, or didn't, amid tough circumstances. This remains conjecture, of course. It's bridging voids with layers of guesswork. Yet the chemical evidence stands firm. A 7.6-to-1 ratio isn't arbitrary. It sets a limit, a key parameter any origin theory must accommodate. Meeting that demands either intense alteration across eons or birth in a realm starkly unlike Earth's cradle. JWST's observations wrapped up in August. The comet drew perilously near the Sun for secure viewing, prompting the scope to pivot to fresh objectives. No scheduled revisits follow perihelion. JWST slots are invaluable, booked far ahead, and the chance to study 3I/Atlas has passed. Any transformations at perihelion, any alterations in chemistry under peak solar flux, will evade Webb's gaze. Ground observatories and JUICE must capture the fallout instead. By that point, the carbon dioxide to water balance could have altered. The coma's makeup might have transformed. The insights JWST gleaned in August may represent our sole glimpse of 3I/Atlas before perihelion. That renders the dataset priceless. A molecular signature from a relic of another stellar realm, forged eons ago. A ledger of volatile contents mirroring inaccessible, unviewable past conditions. And an enigma that intensifies with each scrutiny. For an 8:1 proportion isn't merely odd. It's a beacon, a signal indicating events unfolded here unlike those in our galactic neighborhood. Natural or engineered, chance or intentional. These linger as the enduring riddle. Chapter 5. Mars encounters the intruder. October 3, 2025. 3I/Atlas hurtled by Mars at 29 million kilometers distant. To put it in perspective, that's about 77 times the Earth-Moon span. On astronomical scales, it's proximate. Near enough for ESA's Mars satellites. Devices built to image reddish, iron-tinged terrain just a few hundred kilometers beneath them. Scientists could redirect their equipment toward the heavens and spot the interstellar traveler as it hurtled across the Martian atmosphere at 67 kilometers per second. The ExoMars Trace Gas Orbiter delivered the sharpest views. Cassius, the color and stereo surface imaging system, snapped a sequence of shots from October 1st through the 7th. These photos don't dazzle like Hubble's masterpieces. In them, 3Atlas shows up as a blurry white speck, a bit stretched out, drifting over a backdrop of streaking stars. The stars blurred due to Cassius following the comet's path, adjusting for its speed compared to the probe. Every shot lasted 3 minutes. Combine them, and you end up with a basic moving picture. The speck slides down the view, its coma standing out as a hazy glow spanning thousands of kilometers. Nothing resembling a tail appears, or at least none vivid enough to cut through the background clutter. Nick Thomas, the lead investigator for CAS, conceded that the effort was tough. The comet shines about 10,000 to 100,000 times dimmer than their typical subject. That subject is Mars itself, a world bouncing back sunlight from nearby. Aiming the identical camera at a faint comet 30 million kilometers distant feels like peering at the distant skyline through a magnifying glass. The tool wasn't built for such tasks. The timing for exposures doesn't fit. The detection range is barely adequate. Yet they succeeded. A scatter of pixels, a patch of glow. Proof that 3 Atlas sat precisely where calculations predicted, behaving just like a comet nearing the sun ought to. The veteran Mars Express orbiter from ESA tried its hand too, but the comet stayed too subdued. Its high-resolution stereo camera yielded zilch. The Omega and Spicum spectrometers hunted for telltale light patterns, yet the signal strength drowned in the noise, preventing clear results. They may have glimpsed a trace, perhaps a weak glow line or a slight dip in the spectrum, but the findings remain unclear and tentative. Mars Express's true contribution lies in the surrounding setup, pinpointing the probe's position, the exact moment it observed, and the precise area it scanned provides key limits. Should 3 Atlas have shed smaller bits during its pass, should chunks break off the core, Mars Express would have detected them. The absence of anything beyond the main body indicates no breakup happened then. The comet held together. NASA's Mars satellites kept an eye out as well. The Mars Reconnaissance Orbiter, equipped with its high-rise camera, boasted the detail to possibly photograph the core head-on if the angles cooperated. At a nearest pass of 29 million kilometers, that yields about 30 kilometers per pixel for high-rise. With the core sized at 5 to 6 kilometers, it's just shy of a full pixel. The core would register as a flare of brightness, a lone saturated pixel amid the fainter surrounding haze, but it ought to show up if the settings matched and the aim was spot on. Up to the time of this report, no high-rise pictures have surfaced publicly. That's standard procedure. Handling data from Mars orbiters demands patience. Shots pile up, transmit down when slots open, run through adjustment processes, and finally hit the open databases. Delays of weeks or months are routine, yet the holdup has sparked rumors. Parts of the web claim NASA is hiding info. That high-rise spotted something odd, and the photos are under secret review before any announcement. That's baseless. NASA operates differently. The Mars projects are open initiatives with set data-sharing rules. All material emerges in time. The weight stems from logistics, not cover-ups. Still, the buzz points to a key shift. Folks are tuned in. 3 Atlas has gripped the public's interest far beyond what 1I/Oumuamua or 2I/Borisov achieved. Perhaps the schedule plays a role. Or Avi Loeb's bold ideas supply a storyline that draws in science fiction lovers. Or social platforms have evolved, pushing obscure subjects into broader spotlight. For whatever cause, the October 3rd close encounter transcended astronomy. It became a societal highlight. Individuals who've never peered through a scope now ponder paths in space, light breakdowns, and what sets a comet apart from a crafted relic. The Perseverance rover, parked in Jezero crater by NASA, gave it a go too. Its Mastcam-Z lenses can photograph sky features on Mars, stars, Phobos, Deimos, solar occultations. Theoretically, they might snag 3I/Atlas if the brightness and elevation worked during the rover's active periods. On October 1st, a few Mastcam-Z frames picked up a subtle line overhead. Simeon Schmitz, an astrophotographer, layered those frames and boosted the visibility. The outcome reveals a blur right where forecasts put 3I/Atlas. It's far from conclusive. It might simply be interference from cosmic rays. Or perhaps artifacts from image compression, though the spot lines up perfectly. The sequence fits too. And should it turn out to be genuine, this would mark the sole surface-level glimpse of an interstellar visitor snapped from an alien world. Avi shared it online, pointing to it as proof that the comet could be followed, monitored, and detected by current tools if only we aimed them correctly. Skeptics fired back. The mark was barely there, open to interpretation. Bold assertions demand ironclad proof, and a blur plus a composite photo falls short. Yet the argument holds worth. It compels folks to dive into the evidence, scrutinize what counts as solid fact over mere chance, and wrestle with the doubt that shapes the frontier of exploration. China's Tianwen-1 probe and the UAE's HOPE mission were also orbiting Mars at the time of the pass, each equipped with imaging gear and analyzers. In principle, both had the capability to spot 3I/Oumuamua. Wait, the text says 3 Atlas, so preserve that. No readings from those efforts have surfaced so far. Tianwen-1 follows distinct protocols for releasing info compared to NASA or ESA. Findings trickle out via research publications and announcements on schedules that clash with Western norms. Hope shares more openly, yet its core focus is Mars' atmosphere, not tracking distant wanderers. Should valuable insights come from either craft, they'll emerge in due time. But quiet doesn't prove nothing happened. That's just how global space efforts work. Cooperation's spotty, and agendas differ. The Mars encounter was bound to be fleeting, a narrow chance when alignments clicked and sensors could glance upward prior to resuming routine tasks. Still, that quick look verified key aspects. 3 Atlas remained whole. Its envelope of gas and dust was bustling and clear. The path aligned with forecasts, give or take observational margins. No breakups, no extra pieces, nothing hinting at more than one icy body on a hyperbolic path behaving as expected. Save for a single overlooked point that stays unspoken in public but simmers in hushed talks. The envelope exceeded projections. Given the sunlight intensity there and the projected core dimensions, it ought to have spanned roughly 2,000 to 3,000 kilometers across. CASIS shots indicate 4,000 to 5,000 kilometers. Not a massive gap. Sizing the coma is tricky at best. It hinges on imaging duration, sensor performance, and where you draw the line between the glow and the void. Even so, it's bigger than simulations suggest, outsized if vapor release ties straight to solar warmth. What accounts for the excess? One idea: the core's more lively than thought. That 8% active area could be an underestimate. Perhaps 10% or 12% is spewing compounds, fueling a broader haze than anticipated. A second possibility: the surrounding ice rubble plays a role. Those drifting bits in the envelope, each vaporizing on its own, swell the zone of activity past the central body. The third notion, the one avoided aloud but bubbling up in off-record chats, posits that 3 Atlas acted up near Mars, ejected stuff, expelled fumes, executed a shift that boosted envelope output for a spell. Zero backing for this third angle. Zilch. Yet no proof doesn't rule it out, and the Mars pass was the final sharp view before closest solar approach. If changes were afoot, if instruments launched, bits split off, or the comet shifted from quiet to lively, that proximity made sense. Near enough to a world for intrigue, distant enough from the sun for thrifty actions, shielded from Earth-based eyes, but in sight of Mars-based probes. Spotting a routine comet with a modestly enlarged envelope via the Mars satellites brings both comfort and irritation. Comfort in lining up with predictions. Irritation since the modest enlargement leaves room for varied theories without nailing down one. There's another Mars tidbit awaiting deeper review. The Trace Gas Orbiter's Nomad instrument didn't merely photograph 3 Atlas. It gathered spectral readings, crude ones, muddled by stray light and gear glitches, but readings all the same. Processing continues. The group tackles alignment hurdles, aiming to pull a clear trace from captures not designed for such a dim, swift quarry. Success here, if Nomad snagged emission signatures from the envelope amid the pass, yields makeup details from an angle unlike JWST, Hubble, or SphereX views. Unique sightlines, lighting angles, glow setups. Compounds appearing in Nomad's output could match prior scans. Compounds absent their things absent from the expected patterns, but present nonetheless, turn out to be fascinating. Insights won't emerge overnight. Spectral examination demands meticulous effort. Countless hours spent sifting valuable insights from barely adequate datasets. Yet the researchers remain driven. This represents the sort of data collection that shapes professional legacies. A rare opportunity to examine an interstellar comet via observations from Mars orbit at its nearest pass. Should they derive significant findings from those cluttered spectral readings, the delay will prove justified. Mars offered an additional benefit: a trial run for the alignment and synchronization procedures. 3-2 Atlas traveled swiftly, at 67 kilometers per second with respect to the Sun, albeit more sluggishly relative to Mars owing to gravitational dynamics. Directing a probe sensor toward a fast-moving object calls for exact positional data, instantaneous adjustments, and flawless synchronization. The Mars satellites executed it flawlessly. CASIS framed the comet precisely in the middle of the image. Such achievement confirms the techniques. It demonstrates our ability to synchronize data gathering among various probes and organizations, all aimed at a fleeting target with no room for retries. And that's crucial come November. As JUICE monitors post-perihelion activity, the teamwork will matter even more. The comet may shine brighter, yet exhibit greater activity, possible breakup, or inconsistent behavior. JUICE demands precise positional info refreshed live, drawing from terrestrial sightings and trajectory computations. The Mars encounter served as the final practice. JUICE marks the primary spectacle, with every lesson from the October 3rd data runs, each alignment technique, adjustment protocol, and analysis workflow, directly enhancing the November observations to maximize their scientific yield. 3I Atlas has departed Mars' vicinity. The alignment has altered. The comet has ventured farther into the solar system's core, nearer the Sun, more distant from the Crimson World. The satellites have resumed their standard operations, charting terrain details, probing air chemistry, hunting for hidden ice reserves. The fleeting interruption from an extrasolar guest has faded, leaving Mars solitary in its path, poised for whatever extraterrestrial brush comes next. Chapter 6. Could it disintegrate? Comet breakup occurs frequently. It's hardly an anomaly. Numerous comets have shattered throughout documented annals. Some with dramatic flair, others subdued, yet all adhering to mechanisms that scientists grasp fairly solidly. Heat-induced strain fractures the core. Gas release builds internal strain. Spinning motion and gravitational pulls tear apart loosely held components. What was once a unified comet morphs into a dispersed comet cluster. We record it, dissect it, and file it among the entries of bodies unable to endure their solar grace. 3 Atlas bears no duty to endure. This point merits emphasis. It's a body unified by such feeble gravity that a casual stroll could break free from it. An entity that has endured extreme temperature swings from nearly absolute zero to the mild heats it faced over eons drifting through the cosmos. An entity riddled with pores, cracks, and empty spaces where gases once resided before vaporizing in prior star systems we remain ignorant of. Its structural stability remains dubious. Its unity hangs by a thread. The gravitational hold maintaining the core's wholeness registers in mere newtons, far from megatons. Thus, the issue isn't if 3I Atlas might fragment. It's if it shall, and the outcome depends on variables beyond earthly detection. Consider past examples. Shoemaker-Levy 9 stands as the renowned instance, spotted in 1993 already split into over 20 separate chunks aligned like beads along its path. The split occurred in 1992 amid a near flyby of Jupiter. Gravitational stresses surpassed the comet's binding resilience. The core tore asunder. When we first observed it, the division was total. 18 months on, those pieces slammed into Jupiter in a chain of strikes that scarred the planet's atmosphere for months. The biggest chunk unleashed power akin to 6 million megatons of TNT. Not via blasts, merely through motion energy. Mass times velocity squared over 2. The laws of nature show no mercy for unease. However, Shoemaker-Levy 9 belonged to the Jupiter orbit group. Compact, feebly cohesive, already compromised by prior loops. 3 Atlas measures larger, more compact, and this marks its sole venture into the inner solar system. Distinct conditions, distinct hazards. Comet 73P/Schwarzmann-Watchman 3 broke up in its 1995 return, then shattered further in 2006. Each solar skim shed fragments. By 2011, surveys identified over 60 separate bits, mostly minuscule, each tracing near-identical paths, nudged askew by the speeds gained in detachment. The original core persists, circling still, but reduced, worn down, shedding substance per perihelion until at last only a rubble trail lingers, primed to spawn a meteor display should Earth intersect that trajectory ages hence. Comet C/2 Comet C/2019 Y4, Atlas, oddly bearing a partial namesake with 2I/Borisov, yet bearing no connection whatsoever, broke apart back in April 2020. As it neared its inaugural perihelion, the object grew brighter just as anticipated, stirring buzz among hobbyist stargazers who hoped it would shine bright enough for unaided viewing. Suddenly, though, it dimmed at an alarming pace. In mere days, what had been a solid core transformed into a diffuse haze of minuscule pieces impossible to distinguish one from another. Observations from Hubble captured the disintegration. The debris dispersed, grew fainter, and eventually vanished. The comet no longer existed as a unified body. The cause of C/2019 Y4's shattering remains a mystery. It hadn't ventured too near the Sun at that stage. Disruptive tidal effects were minimal. Its spin wasn't unusually rapid. Experts leaned toward thermal strain as the culprit. Intense warming on the sun-facing surface contrasted sharply with the frozen darkness on the opposite side, leading to uneven swelling. This disparity fractured the core. With the initial split in place, escaping gases widened the fissure. Sublimating ice generated forceful bursts that hastened the tear. The breakdown snowballed quickly. In a matter of hours or days, the whole structure collapsed irreparably. Might something similar befall 2I/Borisov? Without question. The heat disparity at perihelion promises to be intense. One flank scorched by unrelenting sunlight, the reverse in perpetual chill, scarcely touched by warmth. Across a core spanning just 5 to 6 kilometers, temperatures could vary by hundreds of Kelvin. Such extremes breed structural tension. Factor in the buildup from carbon dioxide turning to gas, occurring precisely under the conditions 2I/Borisov will face, and the setup mirrors a perfect storm for disintegration. Yet a rebuttal exists. 2I/Borisov has displayed activity for months, traceable to at least June via prediscovery photos revealing a subtle envelope. Ongoing gas release has vented built-up stress, gradually wearing down its exterior. This measured weathering could ironically avert a total collapse. Imagine it as a built-in safety mechanism. Provided vapors can seep out consistently via surface openings and fissures, internal forces stay below critical thresholds. The comet discards its ices in a steady fashion, shedding weight while upholding its framework. Evidence comes from its spin cycle, 16 hours, steady without acceleration or deceleration. Uneven venting or lopsided jets would alter the spin through applied twists on the core. The unchanging rate implies even gas expulsion and uniform wear. The body isn't ripping itself asunder through its emissions. Size plays a role too. Bigger comets resist breakup more stoutly. Self-pull grows with volume, while resistance to tearing ties to surface dimensions. For something 5 kilometers across, composed of loosely packed snow and grit, gravitational hold prevails. Outflow speeds are low, mere meters per second, yet sufficient to bind the loose aggregate against spin and routine venting. Escaping that grip demands a strong jolt. A violent surge, an impact, or a gravitational brush nearer than what 2I/Borisov will endure. Barring pre-existing fissures or a fragile heap reliant on mere rubbing rather than solid bonds, minor strains alone won't suffice. In such a weakened state, though, subtle pressures might spark division. The pieces wouldn't burst outward dramatically. Instead, they'd wander apart leisurely, their orbits subtly diverging over days and weeks. Viewed remotely, the comet would seem to blur, its center losing definition, the surrounding glow turning uneven, with eventual hints of distinct clumps, separate brightness spikes, each piece tracing a path akin to but distinct from the parent bodies. Indeed, XMR snapshots from October 3rd reveal no signs of splitting then. The core shows as a lone luminous spot, though clarity was limited. Fragments mere kilometers apart would blend into a single vague patch for Cassis. Verifying wholeness requires sharper views after perihelion, a job for JUICE. Now, ponder Lowe's contrasting view. Suppose the splitting isn't haphazard? Imagine it's purposeful. A central craft hitting perihelion and dispatching numerous scouts would mimic, from afar, a comet succumbing to heat-induced failure. A single form yields to several. They trace spreading paths. Their glow shifts as they rotate, altering sunlit profiles. Every aspect fits natural decay. Every bit could also stem from calculated release. The key lies in subtleties. Organic debris adheres to inertial paths. Position stems solely from separation speeds and ambient gravity. Newtonian rules let you forecast each piece's location precisely. No deviations. Engineered craft, conversely, can adjust course. Equipped with drives and navigation. In interstellar objects, a key indicator is their capacity to alter course following detachment. Should pieces emerge that stray from anticipated ballistic trajectories, speeding up, slowing down, or veering off, that signals a technological marker, clear and irrefutable. Lowe has dubbed this the dandelion theory, a central vessel releasing offspring. Every offspring serves as a scout equipped with detection gear and transmission tools. The organic parallel is intentional. Dandelions don't strategically position their offspring. They fling them into the breeze, banking on volume rather than accuracy. The majority settle in barren ground and perish. A handful encounter ideal spots and flourish. For an advanced society probing the cosmos, the approach mirrors this. Launch countless scouts. Many malfunction or detect no value. Several hit pay dirt and relay findings. The expense for each scout remains minimal. The rewards could be vast. Should 3I/Atlas adhere to this pattern, perihelion marks the release phase. The scouts fan out. They harness solar gravity alongside their onboard drives to head for designated worlds. Earth, Mars, Venus, perhaps Europa or Enceladus if the objectives encompass frozen satellite examinations. Every scout targets a precise site with sufficient propellant to get there. Over the course of weeks or months, they touch down, commence monitoring, send reports to the parent craft prior to its departure from the solar system out of signal reach. From Earth's vantage, it resembles a comet splintering. We dissect the segments, compute their paths, issue studies on heat-induced strain and material breakdown. Yet we overlook the true narrative unfolding live because we presume ordinary mechanisms when an alternative unfolds. That's Lowe's dire vision. Not merely that 3I/Atlas is artificial, but that it is artificial and we misconstrue the clues due to overlooking the proper indicators. We've devoted ages to comet research. We recognize fragmentation patterns in comets. Such expertise skews our analysis. Spotting debris, we default to organic explanations. Breaking free of that preconception demands focused work, proactive hunts for irregularities, more rigorous monitoring of debris than for a standard comet split. Seeking path shifts, thrust indications, any divergence from inert flight. JUICE will handle portions of this on its own. The probe monitors dynamic objects. It computes positional forecasts. If a segment veers from expectations, the monitoring system alerts, though it anticipates minor shifts from vapor emissions, not major adjustments via engines. The bar for spotting oddities suits natural bodies. If that bar proves keen enough to detect scout launches remains unclear. No one has trialed it. No one has required it. One additional factor arises. Whether 3I/Atlas disintegrates organically or by design, we forfeit the main subject. Debris glows fainter, tougher to follow. Spectral analysis grows trickier as the light disperses over various items. The chance to examine a whole extrasolar core vanishes. Purely from research angles, splintering represents the least favorable result. It denies us pure insights into makeup, form, mass. Instead, we face a rubble haze, fascinating on its terms, but far from the untouched specimen we anticipated. Yet if it holds together, if 3I/Atlas endures perihelion as a unified whole, we secure that specimen. JUICE scrutinizes it in November. Earth-based scopes capture it in December. We follow it beyond Venus, beyond our orbit, toward the asteroid zone and farther. We observe its dimming as separation and waning sunlight halt the emissions. We record the tail's transformation, the envelope's fade, the slide back to quiescence, gleaning all possible knowledge before it traverses Jupiter's path in March and vanishes eternally. Thus, the dilemma persists. Will it fragment? Resolution comes in November as JUICE gains its initial unobstructed post-perihelion glimpse. When we discern if 3I/Atlas remains singular or has multiplied, if the core persisted or crumbled, if this tail concludes in a faint scatter of remnants or persists with a solid comet bearing its mysteries into the outer void. Chapter 7. The 10 Billion-Year Voyage. Zabia Perez Cuddo and colleagues at the University of Acarana retrotract the path. 10 million years of orbit simulations drawing on Gaia measurements of star locations and motions. Their quest targeted near misses. Stars potentially disrupting 3I/Atlas over its extended galactic wander. Stars that might trace to its birth system. What emerged instead proved more disturbing. Zero disruptions. 93 prospective star brushes pinpointed, 62 rated as strong certainties. None altered the comet's route significantly. Consider the implications. 10 million years navigating the Milky Way's plane, across zones dense with stars, gas nebulae, molecular interstellar wanderers like 3I/Atlas barrel through dense star clusters and winding spiral arms, regions of maximum stellar crowding where gravitational tugs are impossible to evade. Yet this rogue comet surged right through them virtually unscathed, akin to a projectile racing at 60 kilometers per second against the local standard of rest. Its speed outpaced any gravitational traps, rendering capture futile, while its bulk shrugged off radiation pressure's attempts to veer it astray. Pure inertia propels it onward along a trajectory that's held steady for durations exceeding the span of human history. Speed defines its essence. In the galactic reference frame, 3I/Atlas travels at 58 kilometers per second. By contrast, the Sun circles the Milky Way's core at about 220 kilometers per second. Nearby stars typically cruise at comparable rates, varying by 20 to 30 kilometers per second. But 3I/Atlas isn't merely in motion, it's deviating sharply. Its path diverges from the surrounding stellar stream, bypassing the disciplined spin of the galactic disk. Instead, it slices across that spin at a sharp incline, signaling origins in a realm with distinct motion patterns and orbital traits. The thick disk emerges as the prime suspect, that layer of veteran stars enveloping the slender disk that houses our Sun. These thick disk inhabitants arose in the galaxy's turbulent youth, back when the Milky Way was compact, disorderly, and far from the elegant spirals of today. They traverse with elevated speeds at right angles to the galactic plane, plunging through the disk's layers up and down rather than lingering within its bounds. On average, their metallicity runs lower, forged from primordial gas untouched by successive supernova enrichments. Simulations by Matthew Hopkins and the Ottawahi-Oxford Group, drawing on galactic architecture and motion models, yielded population estimates. Their findings, released as a preprint soon after the comet's detection, pegged a 2/3 chance that 3I/Atlas hails from the thick disk. No ironclad guarantee or empirical validation, just a probabilistic estimate rooted in path tracing and speed alignment. In astrophysics, though, 2 to 3 odds signal strong assurance, sufficient for crafting theories and forecasting outcomes. Should 3I/Atlas indeed stem from the thick disk, it's ancient. Starbirth there halted roughly 10 billion years back. A comet flung from such a thick disk world would have roamed for the bulk of the universe's present lifespan. Our own solar system clocks in at 4.6 billion years. 3I/Atlas might dwarf that by double. It could date to when the cosmos was under 4 billion years along, amid a surge in star-forming activity galaxy-wide. Back then, the starry backdrop differed vastly from today's vista. A full 10 billion years marinating in the interstellar medium. A decade of cosmic ray assaults. Galactic cosmic rays, high-energy specks boosted by supernova blasts and quasar jets, pummel the comet's exterior at near-light velocities. Every strike unleashes energy, snaps molecular links, and ejects atoms across eons, where builds up relentlessly. Outer crusts dissolve, compositions shift, ordered ice crystals devolve into disordered glass. What began as fresh frozen remnants of a newborn planetary disk morphs into irradiated debris scarcely echoing its birth state. That said, deep interiors dodge such ravages. Cosmic rays burrow only so deep. In icy material, a standard galactic cosmic ray proton halts within meters, perhaps dozens for the most vigorous ones. A 5 km wide core offers ample buffer. Its heart, shielded by surface overburden, stays immaculate and unmodified. A frozen archive safeguarding the elemental makeup of a stellar nursery from the Milky Way's infancy. This elevates 3I/Atlas to unparalleled scientific value. It's more than aged. It's a tangible relic of the galaxy's dawn. A fragment of a protoplanetary disk that birthed a comet as the thick disk teemed with stellar nurseries. Our grasp of that era relies on proxies. Photons from far-flung galaxies revealing the ancient cosmos, chemical dissections of Milky Way veterans to deduce early interstellar soups, or computational recreations of galactic growth that align with data yet brim with ambiguities. 3i/Atlas stands as a concrete specimen. No model, no remote glimpse. A real entity we can train observatories on, bearing molecular imprints from its genesis. Isotopic balances, carbon-based compounds, ice crystal patterns, all encode details of that ancient disk setting. In this light, the CO2 to water proportion gains extra weight. An 8:1 mix isn't merely odd, it imposes limits on the birthplace. It hints at a host system with peculiar traits, elevated carbon stores versus oxygen, or a temperature difference across the protoplanetary disk positioned the comet's birthplace past the carbon dioxide frost boundary, yet in an area rich with carbon. Such circumstances could occur frequently in dense disk environments, or they might prove unusual. We lack the data to say. 3i/Atlas marks our initial encounter with a comet from a thick disk. With just a single example, it's a vast improvement over having none at all. Prior to 3i/Atlas, our understanding of thick disk planetary leftovers relied entirely on theory. Simulations suggested that those old stellar setups hurled out comets and asteroids much like contemporary ones. They indicated that a portion of such debris would roam the galaxy for billions of years. They forecasted that, now and then, by pure chance, but predictably, one might venture into our solar system. 3i/Atlas bears out those forecasts, bolsters the simulations, and demonstrates that the primordial galaxy was busy crafting planets and comets while undergoing the chaotic orbital interactions seen in star systems now. The path calculations uncovered a finer detail as well. 3i/Atlas travels nearly at right angles to the Milky Way's plane. Its speed along the z-axis, the vertical offset from the plane, stands out as exceptionally strong. That's typical for thick disk items. Yet it also implies the comet has bobbed vertically across the galaxy for billions of years. Every cycle spans tens of millions of years, rising through the thin disk, venturing into the galactic halo, descending back through the disk, then ascending once more. A sinusoidal route exposing 3i/Atlas to wildly varying conditions throughout its existence. At times, it navigates the crowded disk zones buzzing with star birth and frequent supernovae. There, radiation surges and dust collisions multiply. The comet wears down more quickly. Other times, it drifts in the halo's vast voids between galaxies, where radiation fades and collisions dwindle. The comet enters a quiet phase, where nearly halts. This alternation between punishing and gentle settings could account for 3i/Atlas enduring 10 billion years. The halo intervals allowed recovery, halting mass loss and shielding its core from the constant abrasion of spacefaring. Shakru, Kakarov, and Avi released a study comparing them, 1i Oumuamua, 2i Borisov, and 3i/Atlas. 3 visitors from beyond, each with distinct beginnings. Oumuamua hails from the thin disk, perhaps just 1 billion years young. Borisov sits in the middle at about 1.7 billion years, also thin disk. 3i/Atlas, the elder, clocks a median of 4.6 billion years but could be far older, originating in the thick disk. The variety dazzles. It shows interstellar wanderers form no monotonous group. They hail from all corners, every era, every galactic sector, each bearing its unique tale. And if such range appears in the mere 3 we've spotted, picture the breadth of the whole assemblage. The Verisi, Rubin Observatory, once up and running, should spot dozens of these interstellar intruders annually, possibly hundreds. Every find will reveal a backstory, a starting point, a galactic journey reconstructible via computer models. We'll compile an inventory, chart the spread of expelled planetesimals throughout the Milky Way, pinpoint which stellar architectures excel at flinging stuff into the void, and identify which galactic areas feed the most drifters. 3i/Atlas serves as the pioneer, the specimen proving we can perform this cosmic detective work, spotting a comet in July and, by October, forming a solid guess at its source and age. The margins for error are wide, stretching across billions of years. Still, the approach holds up. Combining orbit computations, demographic simulations, and chemical breakdowns yields an origin narrative. Flawed for now, but open to refinement. Periscuto alludes to yet another consequence without dwelling on it. Having journeyed 10 billion years, 3i Atlas has crossed paths with numerous other star systems, countless ones. The galaxy spins. Stars shift positions. Across 10 billion years, the comet has come within light years of thousands, even millions, of stars. Certain stars hosted planets. Certain planets may have nurtured life. And 3i Atlas glided past those setups unseen or overlooked, hauling its payload of primordial ice to the following rendezvous. This prompts an unspoken query. If 3i Atlas brushed other societies, if it threaded their solar realms as it does ours, what ensued? Did they detect it? Did they examine it? Did they dismiss it as mere space rock? Or did they act differently, plant a beacon, hitch a device, repurpose it as an interstellar signal hub? We hold zero proof of such things. Zilch. But lacking proof doesn't rule out occurrences from a billion years back, around. Galaxies swirl with countless worlds and distant suns we can scarcely pinpoint. This interstellar wanderer, dubbed 3i/Atlas, might bear hidden signals, information, or innovations left by ancient societies that flourished and vanished long before our planet cooled from its fiery origins. We'd remain oblivious without a deliberate, focused examination, open to ideas that seem outlandish at first, until you factor in the vast timelines and see that unlikely doesn't mean unattainable. A span of 10 billion years stretches infinitely. It's ample for realms to emerge and crumble, for life forms to develop sentience and then fade away, for whole clusters of stars to ignite and extinguish. 3i/Atlas has journeyed across every epoch of that saga, a quiet observer of cosmic chronicles. And for a fleeting span of months, it's traversing our neighborhood, offering a single window to decode the tale etched in its makeup, form, and perhaps alterations we've overlooked simply because we haven't sought them. Its path veers by Jupiter come March, then stretches outward past the asteroid zone, the Kuiper region, and the heliopause where sunlight yields to the void of space between systems. Returning to obscurity, resuming its eternal voyage amid the stars. Already 10 billion years in motion. Another 10 billion ahead, until the Milky Way reshapes itself unrecognizably. And 3i/Atlas will persist, gliding onward, safeguarding its enigmas, awaiting the civilization that finally spots it. Chapter 8. Experts mount a fierce defense. Tom Statler pulled no punches. As NASA's top researcher on minor solar system bodies, he faced a direct query about the artificial relic theory at a press conference. His reply cut straight. It appears to be a comet. It behaves like one. It mirrors known comets in nearly every aspect imaginable. He stressed the very for emphasis. This wasn't cautious evasion. This was a researcher setting boundaries and declaring a halt. The irritation among astronomers runs deep. Not due to the inquiries themselves. Inquiries are welcome. They're the fuel of science. The real aggravation stems from the distortion of those inquiries. From how a slim chance idea gets elevated by news outlets and online forums to rival the overwhelming proof of a mundane source. From how each fresh datum, each spectral reading, each photo must navigate the extraterrestrial gadget storyline before genuine analysis can proceed. Chris Lintott from Oxford was sharper still. He dismissed the tech theory as utter rubbish propped up on spindly legs, a slight against the compelling efforts to grasp this visitor. Lintott helped link 3i/Atlas to the galaxy's dense disk. He's devoted months to scrutinizing its path, modeling object distributions, and releasing findings that deepen our grasp of stellar movements and rogue body sources. Yet he sees those efforts eclipsed by splashy stories of alien flagships and tiny scouts. The astronomer's commitment to methodical study gets drowned out by conjecture that demands zero proof and yields no verifiable forecasts. Jason Wright of Penn State opted for a measured tack. He penned an in-depth online essay, dismantling each of Avi Loeb's purported oddities one by one, dataset after dataset. Wright isn't opposed to hunting techno-signatures. He pursues them actively. He's embedded in the effort to detect alien minds. But he's a meticulous researcher who upholds rigor. By his benchmarks, 3i/Atlas flunks across the board. Consider the luminosity puzzle first. The assertion that initial light measurements implied a 20-kilometer span, too vast for a natural body, so it had to be artificial. Wright highlights this as selective data use. Those preliminary scans were coarse, captured when the object was dim and remote. With superior tools and extended views, estimates settled at 5 to 6 kilometers. That's standard data sharpening, not an enigma needing wild theories. The supposed lack of cometary markers in preliminary spectra. Wright reviewed the studies closely. The readings were borderline. Signal strength hovered just over the bare minimum for detection. No distinct chemical bands, didn't signal bizarre makeup. It signaled the object was too subdued for solid analysis at such range. When JWST and top telescopes zeroed in, the hallmarks emerged. H2O, CO2, CO, carbonyl sulfide, all precisely the lineup you'd anticipate from a comet. The early vagueness was a matter of equipment constraints, not inherent traits. The path odds at 0.005%. Wright crunched the figures anew. The math hinges on your close encounter criteria. Factor in practical spotting limits, like only detecting brighter objects, and the odds climb notably. You're not gauging the chance of just any stray passing close to 3 planets, you're assessing the chances that a detectable object would swing by 3 planets. That's a far less stringent requirement. The likelihood remains slim, yet it's not ridiculously improbable. It's nowhere near 5 sigma levels of oddity. Regarding the dust setup, the assertion that dust blowing toward the sun demands powered engines or deliberate releases doesn't hold up. Wright draws on years of comet research to highlight how dust patterns get intricate. Jets don't fire evenly. The object's spin axis plays a role. Differences in frozen materials nearby lead to uneven vapor releases. The particular arrangement observed in 3I/Atlas could stand out, yet it fits inside the spectrum of ordinary processes. Scores of comets in our solar system display comparable traits. No one calls an extraterrestrial engineering to account for those. Close examination unravels the spin duration claim. A 16.16-hour cycle is typical for an object of this scale. It resists falling apart. It aligns with structures like loose aggregates or intact bodies. It reveals zero clues about engineered versus organic beginnings, since both exhibit parallel spinning traits. Treating it as proof of advanced tech is akin to declaring a stone man-made just because it's spherical. Sphericity might arise naturally or through crafting. Spin rates might evolve organically or by intent. The data point stays neutral. Wright levels his strongest rebuke at the trajectory origin debate. The idea that arriving from Sagittarius toward the galaxy's core cleverly dodges initial spotting smacks of imposing purpose on mere layout. 3I/Atlas entered from there simply because that's its path. Had it hailed from Ursa Major, proponents would likely claim that spots superiority for different tactical perks. Such reasoning can't be disproven. Every incoming path could get framed as deliberate. That's narrative, not rigorous inquiry. Yet the gravest flaw stems from what's missing if the idea held water. Should 3I/Atlas represent a crafted device, it ought to give off excess warmth. Powered operations, circuits, or drives all produce thermal output. That energy must escape via radiation. In the infrared bands tied to temperatures around a few hundred Kelvin, scopes should pick up glow beyond mere sunlight absorption. Numerous IR scans have occurred. Spitzer prior to shutdown. JWST, SphereX, plus Earth-based IR arrays. Each reveals heat signatures matching a chilly, frozen form heated solely by the star. Nothing extra, no irregularities, just standard comet fare. Propulsion, if present, would show in spectral lines, chemical traces, or path shifts surpassing gas ejections. 3I/Atlas has faced non-stop monitoring since spotting. Its path is mapped with fine detail. Any straying from strict gravity would stand out. None appears. The object adheres flawlessly to classical physics. No thrusts, no adjustments, no signs of guided motion. Communication, were it happening, should register. Radio waves, laser beams, flickering signals. SETI experts have tuned in. Various radio dishes have aimed at 3I/Atlas en route. The Green Bank Telescope, Allen Telescope Array, Parkes in Australia, all scanning broad spectra for artificial traces. Findings: utter quiet, absolute, without even debatable static to stretch interpretations, merely the cosmos's faint static sans text signatures. All probes to separate artificial from innate causes have run their course. All return voids. Eventually, proof responsibilities change. Mere rare alignments no longer demand nature stretch to fit. You require affirmative signs, a spotting, a reading, something a comet can't justify without tech intervention. Such proof is absent. Statler drove this home clearly. We wield top-tier tools. We've scrutinized 3I/Atlas closely for months. Anything truly off-kilter, any comet-defying trait needing fresh theories or exotic labels, would have surfaced. Its absence counts as evidence, strong evidence, favoring everyday origins. The expert's reaction stays balanced yet resolute. Studies appear, info circulates, watch continues. But a quiet consensus holds that the artificial notion merits no further deep dive. It's undergone trials. It flopped. Lingering arguments divert from the real gems 2I/Atlas offers. Those gems abound. Our initial thick disk comet under the lens, the debut with an 8:1 CO/2:1 mix, the pioneer interstellar guest eyed by JWST, Sphere X, and Mars satellites all at once. Just the makeup of the object itself could sharpen our theories on how planets took shape in long-gone stellar neighborhoods. Tracking its path enhances what we know about how galaxies move and why things get flung out into space. The way it releases gases upends our ideas on how comets act and where their volatile stuff is stored. Yet none of this shines through because the discussion always loops back to talk of extraterrestrial gadgets. Researchers are fed up with wasting effort shooting down ideas that never should have caught on. Fed up seeing their findings overlooked since they're not flashy enough. Fed up with suggestions that they're narrow-minded for demanding proof before buying into wild ideas. What Lind said about feeling insulted hits the nail on the head. The folks handling 3Atlas rank among the planet's top skywatchers. They're wielding state-of-the-art gear, sharing results in premier publications, and carrying out science's core mission. Watch closely, break it down, form judgments from the numbers. Then they're accused of overlooking the plain truth, of clinging so hard to old-school views that they miss what's staring them in the face. It's maddening. There's an even bigger worry here. Folks walk away from this mess thinking experts brushed off the alien angle without a real look. That's flipped around. The probe was deep and thorough. Various groups, different tools, weeks of hard work. They treated the idea with gravity, put it through the ringer, and it didn't hold up. But since the checks were complex and the no-shows didn't make waves, people figure the pros are just brushing it aside instead of digging in deep. That view hurts the field. It feeds the notion that official stargazing is stuck in its ways, scared of big changes, too tied to old models. But that's flat wrong. Sky experts would jump at signs of alien tech. It'd be the find of the century, Nobel nods, books overhauled, our cosmic spot totally reframed. The drive exists, the eagerness is real. What's absent is the backing. Wright nailed it in his online piece. Wild assertions need rock-solid proof, not the reverse. Science doesn't insist on everyday answers or total guarantees before eyeing other options. It builds up clues and chases them no matter the direction. And for now, every clue points to a comet. A quirky one, a fascinating one packed with research gold, but still a comet. 3Atlas gets watched clear through November and December. DO-STA shows up come February. Should anything truly odd emerge? If the after-closest sun checks uncover actions no normal explanation fits, the chatter shifts. Experts adjust. Fresh ideas pop up. Predictions that can be checked get laid out. That's science's engine, data over guesses. For the moment, the tech theory stays what it's been, a long shot with tiny odds, no data to prop it, propped by wishful logic instead of hard facts. And the crew probing 3Atlas keeps at it, logging this standout traveler from the galaxy's outer halo, squeezing out every detail they can till it vanishes into the void again. Alien stories or no, splashy news or not. Because that's the scientist's grind. Chapter 9. Social media erupts. The frenzy kicked off on TikTok. A clip dropped on September 29th, layering intense tunes over generic shots of comets and probes. On-screen words screamed that 3Atlas was barreling toward a smash with our planet. NASA covering it up. Crash date, October 22nd. It racked up 2 million hits in 2 days. Flood of reactions. Folks sketching escape routes, wondering about bugging out, scouting spots near fallout shelters. all from pure invention. The crash rumor was a breeze to knock down. 3 Atlas's nearest pass by Earth sits at 1.8 astronomical units. That's 270 million kilometers, over 1.5 times our orb's reach to the Sun. It stays way clear. The path math is out there for all. NASA shares position forecasts. Basic apps let anyone confirm the route, but truth lags behind terror. The fact-check clips pulled a couple 100,000 looks. The scare reel kept bouncing around. It lingers today, still pulling replies from those seeing October 22nd as end times. Next up, the psychic scans. A profile named New York Crypto King shared on X that they'd psychically probed 3 Atlas. They swore they spotted setups within, tiny organisms tucked in frosty holes. A transmission pulsing at bands we've yet to pick up. The entry spelled out the inside setup, the layout of gadgetry masked as regular rock, and there was a caution that probes would launch on October 29th, releasing microbes into Earth's air as part of a planetary reshaping effort. Remote viewing counts as pseudoscience. Rigorous tests have consistently proven it unreliable. No one possesses the ability to psychically observe far-off items, yet the message still gained momentum. It racked up 30,000 likes and 15,000 retweets. Folks accepted it as legitimate intel, weaving elaborate speculations from it, and linking it to broader conspiracy narratives. The assertion about the signal proved especially contagious. Several hobbyist radio operators began scanning bands they believed could host the transmission. They detected zilch, but persuaded themselves the broadcast was coded or employing advanced modulation techniques out of reach for current tech. 4chan jumped into the mix with a thread purporting internal scoop. An unidentified poster, posing as a European stargazer, declared that 3II isn't a comet or spacecraft. Instead, it's a remnant globule of dark matter or energy from the universe's origin explosion. The entity doesn't bounce back sunlight. It draws power from the quantum void. It's barreling our way to fuse with our planet's center and spark a reality-altering transition. Clearly, this was made-up stuff. The science didn't hold water. Dark matter doesn't cluster into spheres. It can't siphon vacuum energy. Still, screenshots proliferated across sites, passed off as pilfered secret docs. The tie-in to Jeffrey Epstein surfaced in early October. A Reddit user spotted that Lowe's initial big study on 3I Atlas came out 72 years post-Epstein's birth. They crunched numbers showing the comet's July 1st fine tied into mystical patterns, tossed in selective links between its path details and Epstein-linked timelines, wrapped up by saying the whole 3I Atlas saga was fabricated to divert from fresh buzz around Epstein's documents. The idea fell apart under scrutiny. Comets aren't unveiled on schedule for agenda-driven plots, but it propagated regardless, merging with QAnon lore and referenced as proof of elite meddling. Alternative spin zeroed in on Lowe himself, with threads alleging his breakdown of 3 Atlas got invalidated due to his Jewish background, Israeli links, or Harvard's cash from foes the writer fancied fingering. These weren't honest doubts. They were prejudice-wrapped jabs mimicking doubt. Lowe countered in a blog entry, stressing 3 Atlas stands on its own merits beyond his background, that telescopes let anyone spot it, and his roots or citizenship don't touch the facts of physics. But battling hate wears you down. The attacks persisted. The NASA closure twist turned into a key debate hook. Early October saw the U.S. government furlough kick off. NASA's comms team halted site and social updates. Bulletins tapered off. This brief info gap overlapped with 3I Atlas nearing Mars and ducking behind the Sun. Theorists spotted intent. The furlough was engineered, a ploy to silence NASA on orbiter sightings from the close pass. Officials were burying evidence, concealing pics of breakups or probe drops, or whatever they aimed to keep under wraps. Truth is, shutdowns stem from political breakdowns, not orchestrated veils. They strike when funding talks fail. The overlap was pure chance. NASA had no secrets. Orbiter info normally needs weeks to sift through. The halt just dragged it out more, thanks to idle workers and stalled workflows, not suppression. Once operations resumed, the photos dropped. They depicted a standard comet, nothing more. Too late, though, the storyline had stuck. Any lag screamed cover-up, no matter the eventual reveal. A laser-centered verification team probed rumors buzzing in Arabic online circles. Threads warned 3i. Atlas would strike Earth on October 22nd, its trail tainting the skies, its pulses frying worldwide gadgets, ancient prophecies foretelling the doom with omens falling into place. Sanard followed the trail to botched renditions and outright inventions, issuing a thorough takedown backed by origins, citations, and specialist input. Their report hit perhaps 10% of the false story spread. A hot Facebook entry alleged 3 Atlas sparked a defense crisis huddle. Global bosses met covertly. Safeguards ramped up. Soundbites from faceless DoD sources hinted the comet threatened security. It pointed to a YouTube clip, 3 million watches, 40 minutes long. The voiceover detailed how 3i Atlas got picked up by secret defense birds before amateur stargazers caught sight of it. The way its path was supposedly hidden at first. The way officials supposedly shared secrets via unofficial routes. None of that held water. Yet it all came packaged with eerie soundtracks and a commanding voiceover that lent it an air of legitimacy. The faith-based perspectives gained traction. Posts from Christians viewing 3i Atlas as a marker of the apocalypse. Allusions to Revelation and the Wormwood prophecy. The comet cast as a messenger of divine reckoning. Muslim writings explored parallel ideas via their own holy texts. Hindu takes linked it to eternal cosmic rhythms and divine incarnations. Folks from every faith tradition layered doomsday tales onto something that's merely frozen water and stone. Humanity's urge to decode heavenly occurrences runs deep in our history. Comets have long signaled doom or change. 3i Atlas fits right in. But these days, such signs race around the world in mere hours, not the decades it once took for tales to ripple through cultures. Online memes played their part. Pictures of 3i Atlas captioned as all sorts of absurdities. Like the assignment I skipped finally catching up to me. Or my troubles landing exactly when expected. Extraterrestrial sightseers scoping out Earth, only to bail after a quick look. Those jokes were lighthearted, even amusing, but they cemented the notion that 3i Atlas was a player in some drama, not just a hunk of space debris. They gave it human-like motives, goals, even a vibe. That personalization clouded people's ability to grapple with the real evidence. Instead of scrutinizing the science, they connected with the comet on a gut level. The divide was sharp. One camp featured experts and outreach folks disseminating solid details. Light spectra, path projections, makeup breakdowns. The opposing wave brought floods of guesswork, plots, dread, and daydreams. The sides hardly intersected. They dwelled in separate digital worlds, on distinct apps, with clashing ways of knowing what's real. Someone could scroll for ages on 3i Atlas content and dodge every reliable detail. X's fact-check tags raced to intervene, attaching explanations to hot posts, directing to NASA resources, supplying path stats to debunk impact fears. But those tags pop up only after the buzz has peaked. The fixes hit just a sliver of viewers. And when beliefs run deep, folks twist facts to fit. Those hooked on the idea of an invading alien fleet brush off rebuttals. NASA's covering up. Experts are too rigid. The straight scoop doesn't compute. Whatever clashes with their storyline gets ignored. YouTube turned into a war zone. Educational creators breaking down 3i Atlas's true nature, the telescope findings, the implications of its makeup. Such clips rarely topped 100,000 watches. In contrast, plot-peddling accounts with flashy covers and hype headlines racked up millions. The system boosts clicks over truth. Panic hooks users way better than plain learning. Thus, the false narratives climb higher, echo louder, and cash in bigger. Reddit threads fractured predictably. The astrophysics and exploration forums stayed grounded. Admins axing wild theories. Members refuting nonsense with sources, fostering polite chats on path ambiguities and light analysis techniques. Yet the UFO, plot, and outlier boards morphed into feedback loops. Doubt earned thumbs down. Ties to established science? Branded as spin. The groups fueled their own extremes, assuring one another they alone saw clearly while the rest were fooled or in on it. Social media stars, sans any astro-creds, dished out bold takes on 3i Atlas. Plenty botched the basics, swapping AU distances for light years, insisting it shone bright without aids when it didn't, blending it with unrelated sky bodies. Still, they commanded followings in the hundreds of thousands, fans who bought in, reposted, and weighed those hunches as heavily as lab-vetted studies. The false info rippled into tangible harm. Outreach pros sifting through frantic messages. Instructors soothing kids convinced doom loomed. Counselors handling stress spikes from end-of-days hype. The fallout wasn't abstract. It showed up in hours burned debunking lies and in real emotional strain on those already fragile. Part of the plot mindset was just edgy pranks. Savvy types stirring the pot for kicks. But plenty was sincere. Devout sorts certain 3i Atlas heralded alien arrival, global peril, or heavenly signs. Challenged, they dug in harder, chasing affirming sources, weaving intricate webs tying 3i Atlas to broader schemes. The thing turned into an icon, a canvas for dumping personal terrors, dreams, or delusions. By mid-October, 3i Atlas had transcended its status as merely a comet, evolving into a societal spectacle that captured how communities digest news in the era of online platforms. The fusion of reality and fabrication, the erosion of expert authority, the rapid dissemination of panic over clarity, all were laid bare. The physical entity itself, that 5-kilometer sphere of primordial ice and stone now concealed by the sun, faded into the background amid the escalating tales encircling it. Researchers examining 3 Atlas could merely observe from the sidelines. They might release studies, offer media insights, issue clarifications online, yet they held no sway over the unfolding tale. The tale had broken free, transformed, and slipped from their grasp. Their only recourse was to press on with the research, record the findings, dissect the measurements, and rely on the enduring truth of the scientific archive, one that would outlast the digital uproar, standing firm against the turmoil. Chapter 10. The pivotal instant in November. On November 4th, JUICE sits 428,000 kilometers away from 3 Atlas, nearer than any probe during the post-perihelion viewing phase. The Jupiter Icy Moons Explorer wasn't crafted for cometary scrutiny. Its purpose centers on probing Europa, Ganymede, and Callisto, frozen shells atop hidden oceans, radiation zones near Jupiter, and electromagnetic dynamics. Still, probes prove flexible. Controllers can adjust strategies. From November 2nd through 25th, JUICE will allocate slots to scrutinize the cosmic interloper, gathering intel while Earth telescopes grapple with the sun's interference. The payload is impressive. Janus, the visible light imaging array, will photograph the core and surrounding haze at unmatched detail for this timeframe. MAGIS, the near-infrared mapper, will chart chemical makeup across spectral bands, revealing volatile spread in the envelope. UVS, the UV analyzer, will capture glows from energized particles and compounds, expanding on August's quick scans, but with sharper resolution. PEP, the environment sensor, will gauge ionized and neutral gases around 3 Atlas, tracing solar wind's influence on its emissions. This phase holds the key. 3 Atlas passed perihelion on October 29th. The effects of that solar close shave, the intense warmth, the surge in emissions, any breakup or device release, will show up in November. The comet ought to shine vividly, erupt actively, perhaps altered. JUICE will capture those shifts from a perspective unattainable by terrestrial gear. Yet limitations apply. Signal capacity. JUICE employs its mid-sized dish since the primary one doubles as thermal protection. Transfer speeds drop. Photos and readings accumulate internally. Retrieval happens later. November's captures won't hit Earth before February 2026. A 3-month holdup. 3 months blind to JUICE's discoveries. Intact survival, splintering, or surprises in the records. Earth observatories should spot 3 icy Atlas by late November, once solar separation widens for dusk viewing. As the glare eases and bigger scopes can engage, estimates differ. Certain forecasts predict magnitude 10 or 11, visible in 8-inch backyard scopes on clear nights. Others temper it to 12 to 13, needing pro facilities or committed hobbyist rigs. Luminosity will reveal drama at once. A sharp surge in 3 icy Atlas's glow, say from a perihelion-induced blast or unveiled ices, means brighter than forecasted. Breakup could boost light short-term via expanded exposure, then fade as pieces scatter. Dormancy, depleted gases, or abrupt quiescence would dull it below projections. Ground checks in those initial evenings will expose it all. The Galileo Initiative stations are active. 3 outposts scanning nonstop: Massachusetts, Pennsylvania, Nevada. Through November and December, sensitivity ramps down. Sudden blips, odd movers get tagged. Lower didn't conceal his hopes. Should probes launch at perihelion, executing retrograde burns for Earth insertion, they'd reach between November 21st and December 5th. The sites hunt precisely for such compact items in odd paths, courses clashing with known junk or sats, hints of engineered design. Odds remain slim, as all admit, but vigilance costs little against the upside. Should anomalies emerge, should and if an unidentified object emerges that defies straightforward explanations, the entire scenario shifts instantly and profoundly. Astronomers worldwide would redirect their instruments to examine it closely. Space organizations would rush to organize flybys or detailed flyovers. The research world would rally with an urgency unmatched since the initial gravitational wave sighting or the breakthrough exoplanet verification. Conversely, should no such entity surface, if November and December elapse without any spacecraft emerging, the artificial origin idea forfeits its final pillar. The anomaly rating plummets. Comet 3I/Atlas earns a firm label as a natural body. Exceptionally massive and compositionally odd, yet entirely organic. The buzz fades. Investigations persist. The narrative pivots to exploration and analysis instead of extraterrestrial encounter. The Europa Clipper mission stands ready for possible sightings too. NASA's Jupiter-bound probe lifted off not long ago. It's en route, but hasn't reached the gas giant. Teams are exploring joint efforts between Clipper and JUICE. Each carries an ultraviolet spectrograph, allowing dual-site views of 3I/Atlas that yield parallax-based 3D insights into the coma, details a lone probe couldn't capture. The alignment isn't perfect. Clipper's vantage isn't prime, but should a window open, operators will seize it. True breakthroughs arise from contrasting conditions before and after perihelion. JWST provided August snapshots, Mars satellites delivered September ones. Those glimpses showed 3I/Atlas nearing its solar closest approach, still chilly, venting modestly. JUICE and Earthbound scopes in November will reveal the consequences. The comet will have warmed, strained, possibly altered by its nearest sun pass in 10 billion years. Matching those records uncovers how such wanderers react to perihelion, how their makeup shifts, how their form endures or crumbles under heat stress. The CO2 to water proportion grows especially compelling. It stood at 8:1 in August. Will November match that 8:1? Or might solar warmth have selectively boiled away the CO2, bearing water ice and nudging the balance toward normalcy? A shift signals layered build, CO2, heavy shell over water-laden core. Stability implies uniform makeup end to end. Either result advances knowledge, though they paint contrasting tales of the object's birth and history. Tail evolution offers another key clue. Pre-perihelion photos revealed a subtle streak, or none, based on imaging duration and gear sharpness. Afterward, expect a vivid streamer, stretching millions of kilometers, warped by sunlight push and path speed. Tail scans disclose ejected particles, silicates, carbon compounds, frozen bits. Particle sizing reveals weathering dynamics. Tiny bits suggest intense vaporization. Bigger chunks point to breakage or bursts. Should 3I/Atlas splinter, the tail gains intricacy, diverse flows, intertwined forms, each piece adding its stream, merging in telescope views yet perhaps separable via precise brightness and location tracking. Hubble might snap the tail's makeup if slots free up, distinguishing piece-by-piece inputs, charting rubble spread. But Hubble slots are gold, booked 5 or 10-fold. Securing emergency director access for a sequel peak isn't assured. The Vera C. Rubin Observatory awaits activation. Its debut glow remains months off, yet once live, it will transform hunts for rogue bodies. The vast survey scope, its old moniker, will sweep the whole night sky every few evenings, with deep scans and instant spotters for transients. Rubin will snag far-off intruders sooner, while dim and distant from the sun. It will follow them past perihelion and further. Compile brightness graphs from thousands of readings. Follow-up spectra via other tools will draw from Rubin's nonstop light tracking. 3i/Atlas serves as the test case. The wanderers schooling us on upcoming interstellar arrivals, what their glow patterns entail, how outbursts progress, which signatures emerge, and precisely when. Each peek at 3i/Atlas shapes Rubin's hunt strategies, hones spotting software, tunes forecasts. The subsequent 3i/Atlas, the fourth such find, will get spotted quicker and probed deeper, thanks to insights from this trailblazer. November's views also sharpen path predictions. Each location fix bolsters the orbit fit, shrinks uncertainty. Reducing uncertainties enables more reliable forecasts for Comet 3i/Atlas's location come December, January, and further ahead. Once the comet advances beyond Venus and Earth's path, steering toward the asteroid belt, monitoring grows more challenging. It fades in brightness and navigates through denser clusters of background stars. Accurate ephemerides guarantee we won't misplace it. That terrestrial observatories can aim precisely. That precious viewing slots aren't squandered hunting for a target that's supposed to appear in the frame but doesn't, due to minor errors in positioning. The plasma readings from JUICE stand out as one of a kind. No alternative probe will approach near enough to probe the interface zone where solar wind collides with the comet's released gases. That frontier, the cometopause, remains fluid, ever-changing with fluctuations in emission levels and solar wind forces. PEP will gauge ion concentrations, electron heat levels, and disturbances in the magnetic field. This information will enhance simulations of cometary magnetic envelopes, the speeding up of charged particles, and the ways energy infuses the surrounding haze. Regarding 3i/Atlas in particular, the plasma insights could uncover nuanced details on its makeup. Various gases break into ions at distinct paces, yielding unique ion types. The PEP's mass spectrometer can differentiate water-based ions, carbon dioxide-based ones, and more. Should unforeseen varieties emerge, or if the plasma mix highlights compounds missed by earlier light analysis, that's groundbreaking knowledge. It tightens our grasp on the true contents compared to estimates from afar. February 2026 seems far off. 3 months is an eternity to hold out for JUICE's findings, yet it's essential. The probe's data link is constrained. Research demands come first, ahead of outreach efforts. The payoff will justify the delay, with the raw feeds refined, adjusted, and scrutinized by specialists familiar with the gear and skilled at pulling clear patterns from the clutter. Once shared in publications, those outcomes will be authoritative. The most thorough post-perihelion profile of 3i/Atlas achievable under today's tech and operational limits. In the meantime, we depend on Earth-based watches, hobbyists peering through home setups, major facilities slotting 3i/Atlas into packed agendas, global teams coordinating spectral studies. Each cloudless evening counts. Each capture enriches the archive. Gradually, through successive photos and light breakdowns, the tale of perihelion sharpens into view. The comet remains indifferent to our intrigue. It has no awareness of our gaze. It merely follows its course, venting vapors or lying quiet, whole or in pieces, ordinary or improbably altered. 3i/Atlas drifts onward through November, unaware of the scopes following its path, the tools probing its glow, the heated discussions over its essence. It simply exists, and we, from our modest spot 93 million miles from the sun, strive urgently to decode that existence before the comet slips into obscurity and carries off its secrets.